Let's start by drawing a nice clear diagram with all the information from the question on the diagram. So a particle P is projected vertically upwards from the point O. So I'm going to label a point O, and it's projected vertically upwards. So it's going to go up like that. The fact that it's projected upwards, it tells us here it's projected upwards with a speed of 12 meters per second. So I'm going to draw the speed of 12 meters per second at that point. Okay, and this is particle P, so I'll label this as, I'll just write it under here, particle P. 1 second after P has been projected from this origin O, another particle Q is projected vertically upwards from O, which means it's from the same point, and with a speed of 20 meters per second. Now, as it's kind of projected from the same point, I could start drawing again from that point O and draw another path for Q, but it's going to be overlaid on top of each other, and it's going to be really hard for me to distinguish between the two. So I'm going to draw it separate next to it at the same kind of horizontal level, so then I can see actually it's projected from the same point. I'm going to label it O so you actually understand that it is exactly the same point, but all I'm doing is I'm drawing it in a different place. But actually they're going to be following the same path if you think about it. It's very important you understand that. This is particle Q, they're calling this, so I'll label particle Q underneath it. And it's projected vertically upwards as well, and this one has a projection initial speed of 20 meters per second upwards. And likewise, this one's going to do the same thing as well. It's going to go up and it's probably going to come down at some point. That's going to go up and come down. It might not go to the same height because this one's smaller velocity, so it'll go up to a smaller height and do something like that. And they will both come and hit the ground if there is no collision between them. But let's go and read on what it actually says. Since they're both released from the same point and they're actually following the same path, the fact that one was released above and then the other one released a second or 1 second after means that they will actually collide at some point. Do we understand that? Okay, let's make sure that's clear first. So I'm posing this as a question. They're both being released from the same point, O. I know my diagram shows that it looks like 2, but no, they're released from the same point. Particle P is released, and then particle Q is projected 1 second after. So that means that as they've both been thrown up, there will be a collision at some point. Are we happy with the fact that there will be a collision? Yes, no? Yeah. Okay, good. So we know there's going to be a collision. We don't know where. It might be that since particle Q is released afterwards with a greater velocity than the other one, it might be that they both collide on their way up. Or it might be that one is on its way down and the other one is on its way up. So particle P might be on its way down and Q is on its way up and it might collide. We don't really know exactly where that's going to happen. But what we do know is there is going to be some collision. What can we say about the point of collision when that collision actually happens? Let's understand something. When they do collide, what will happen? We can say that, any ideas, anyone? If they both collide, they're both released from the same point, O.
The time will be the same.
Will it? One's released 1 second after. Particle Q, I'll write down here, released 1 second. Can't spell second. Oh yeah, I can. Second after. The time won't be the same. Particle P would be in displacement from the origin because they're both released from the same point, O. So if they collide at a particular point, collision means that they are at the same point, aren't they? So suppose they collide here. Let's just say this is the collision line. Then their displacement is the same, right?
I think just to say, he's right, isn't it? Will happen the same time of day, but not in terms of time of how long they've been traveling.
Yeah. Okay, no, that's a good point that you made. Yeah, so at this point, when we talk about the time, the T that we have in SUVAT, S-U-V-A-T, what we've got to understand that T is not necessarily the same time as in the time of day. That T refers to the time in flight. So that's very important to understand. So it's probably worth making a note about that. In SUVAT, that T is the duration between point A and B. If we were considering between A and B. Now here we'll assign some letters here. So we'll call O for both of them as we have starting point, and I'll call the point where they collide C. I'm going to label on both of them C. Now O to C, the time it takes from O to C for particle P and the time it takes from O to C for particle Q is not the same. The duration is not the same. The time of flight is not the same. The time T in SUVAT is not the same. Okay. Yes, they collide at the same instant. So they will collide at 2:20 p.m. but the flight of time is not the same. Okay, but we're interested in the T, which is the flight of time. Clarified? Thumbs up, down?
Thumbs up.
Okay. Right, so let's move on to the question then. We've talked about projected vertical upwards. We've established the speeds. We know that particle Q is released 1 second after. And when they do collide, we want to figure out certain things here. It says here, find the time between the instant P is projected from O and the instant when P and Q collide. All right, let's go and first of all consider applying SUVAT here. Now for particle P, again, I'm going to do two sets of SUVATs because I've got two particles. I'm going to define my starting and finishing point for particle P is from O to C. I'm going to define my direction, which I'm going to take as positive. It is the initial direction of motion. For particle P, it's moving initially upwards, up as positive. SUVAT. I'm going to write down what I know. Do I know what my displacement is from O to C? No. Do I know my initial velocity? Yes, 12. Do I know my final? No. Do I know my acceleration? Yes, it's 9.8, but it acts downwards, which is opposite to my direction of positive, so therefore negative 9.8. Do I know my T? No, but what I'll do is I'll call this uppercase T. Let's go and look at O to C for the second particle. O to C, again up as positive because that's the initial direction of motion. Again, SUVAT. Now let's write down what we know. Initial velocity 20. Initial displacement, we don't know. But what do we know about the displacement from O to C for particle P and for particle Q? You guys said it at the beginning. We said that the displacement is the same. Are you happy with that? So can we then call them both the same letter? I'll call them both S. Are you happy with that? This is a very important point to kind of make sure we stop and pause and think about it. I've labeled them both S. If you're happy with that, thumbs up. If you have any questions, now's the time to ask. Ahmed, are you happy with that? Okay, let's move on then. So what about the velocity of this particle? We don't know. Acceleration, again, it's minus 9.8 because we're taking up as positive.
T+1 for the second OC.
Okay, let's come on to that. Let's think about it. Good work. Someone's asking about Umar. You're asking about would the second one be T+1. So this is where a lot of mistakes happen. Is it T+1 or is it T-1?
Shall I write and get them to vote?
Have a little think. T+1 or T-1? Thumbs up next to T+1, thumbs up next to T-1.
Oh, one vote for +1.
Only one vote. I'm sure there's more of you here.
Yeah,
come on.
It's +1.
Let's have some votes.
Oh, 4 people think it's +1. Dadabai. Azar for him.
Okay, let's understand what's going on here. Remember what I said about T. T is the time that the object is in flight between O and C. And I urge you to understand that T in SUVAT refers to the time of flight between the 2 points that we've labeled. Time of flight between O and C. Now, particle Q starts 1 second later. And when it has collided with the other particle, think about it. Let's say it collides at, let's say, think about it like this. I'm going to assign some time here, clock times. So suppose particle P starts at, let's say, 12 hours, 31 minutes and 0 seconds. And the other one will start then at 12 hours, 31 minutes and 0.01 seconds. Are you happy with that? Because it starts 1 second after. Yeah? Guys, be happy with that? Yeah. Now, when they collide, can we say that because when something collides, if two things collide, then in terms of the clock time, which is what we can say, in terms of the clock time, they will both collide at the same time, right? So let's suppose they collide when collision happens, it will happen at the same time. Suppose it is at 12:31 and 40 seconds, 12:31 and 40 seconds. Are you happy with both of them colliding at the same clock time? I'm referring to the clock time. I'm distinguishing between clock time and the T that we have in SUVAT, because the T in SUVAT is the time which it is in flight. Yes, happy? Because if two things collide, they must collide at the same clock time. Now take a look at the duration it's in flight, the second one, particle Q, and the duration it's in flight for particle P. The duration of flight for particle P, as you can see here, is 40 seconds. And the duration of flight for particle Q is 39 seconds. So now tell me, if we've called the first one's duration T, what is the duration of time for the second one in terms of T? Should we have another vote? Oh, a lot of people are writing T minus 1. Okay, all right, so we're happy with it being T minus 1. Okay, so those people who initially said T plus 1, hopefully you realize, and those people who initially said T minus 1, hopefully you understand why you said that now as well. So this is a common area where mistakes are made though. So it's very important you understand that. If in doubt, just do some clock times like me and then figure out which one's which. Okay, so now that we've established, I'm going to get rid of the clock times because that was actually something which was made up. It's not really 40 seconds and 39 seconds. That was just to illustrate why it's T minus 1. So let's get rid of that, get rid of that. So now we've got two sets of SUVATs involving 4 variables. We can set up an equation involving those 4 variables, S, U, V, A, and T. The things which are equal between the two is the displacement. Why is the displacement the same? Anyone? Why have I called both of them the same displacement, S and S? If you don't answer, nobody else is going to answer. Don't think the other person's going to answer. Write down your answer.
Who should we nominate?
Come on, guys. Why is the displacement the same for both of them? Because they are both from O to C. Well done, Ahmed. Yeah, they both go from the same starting point to the same.
Wouldn't collide, displacement is different.
Displacement could be different and they could collide. We looked at the previous example before lunch where they both started from different points and they collided. So, and they had different displacements, S1 and S2. So they could collide if they have the different displacements. Yeah, but here, because they both start from the same point, and for there to be collide, then they must have the same displacement. Okay, so let's set up our equation involving the 4 variables. For particle P, we're going to use SU, A and T, S equals UT plus half AT squared. I'm going to go straight into the equation and substitution. S, which we don't know, equals U, 12. T for this one is the uppercase T, plus half acceleration minus 9.8 T squared. SUVAT for the second one, S is equal to U, which is 20. T, what is our T here? T minus 1. Okay, be very careful. We're using T minus 1 here. UT plus half acceleration minus 9.8 and bracket T minus 1 squared. Okay, so we've got 2 equations with 2 unknowns, S and T. 2 equations, 2 unknowns, simultaneous equations. Substitute one variable into the other. As both equations are equal to S, if we substitute one S into the other, you will then result in eliminating the S's, and then you'll have an equation involving just T's. So substitute one equation into the other will then get us 20 T minus 1 plus half minus 9.8 T minus 1 all squared is equal to 12 t plus half minus 9.8 t squared. Be careful here. We need to tidy this up a bit, expanding and so forth. When you're expanding 20 t minus 20, I'm going to multiply these two bits first here, minus 4.9, and then my t minus 1 squared. Make sure you don't make any silly errors such as this. This is a silly error, isn't it? You see what I've done here? That's a silly error, right? Just squaring the t and the minus 1. It's the whole bracket squared, so don't forget that. T squared minus 2t plus 1 is equal to 12t minus 4.9 t squared. Okay, again, watch out for mistakes here because I've got minus 4.9 timesing everything inside that bracket. So I'll get minus 4.9 t squared, negative 4.9 times negative 2t, positive 9.8 t plus, negative 4.9 equals 12t minus 4.9 t squared. Now that everything's expanded, collect like terms equate to 0 as we have a quadratic here. Let's see, if I plus 4.9 t squared on both sides, I will actually get rid of these. And if I do 20t plus 9.8t, I'll get 29.8t minus 12t is equal to 24.9. 29.8 minus 12, what's that? 17.8t is equal to 24.9. Therefore, t is equal to 24.9 over 17.8. What's that? .398 to two significant figures. That's 1.4 seconds is what that time is, uppercase T, i.e. the duration of flight for particle P, whereas the duration of flight for particle Q is that time minus 1, if you remember. So let's go back to the question and make sure we've answered. Find the time between the instance that particle P is projected from origin and the instance when P and Q collide. So it's referring to the time of flight for particle P, which is what I've actually worked out. So that should be fine. Okay. Hopefully I haven't made any mistakes with my arithmetic, but I'll just double check that one as well in the book to make sure that value is correct. Chapter 9, challenge 9E. 9E challenge is part A is 1.4 seconds. Yeah, so that's fine. Right, so we've got the first part, and then the second part it's asking for in this question is the distance. Find the distance of the point P and Q where P and Q collide from O. So it's essentially asking for that distance from O. So really, let's mark it in. The distance from O is referring to that. Now here, if where they collide, the distance from there to there is actually the same as the displacement. Okay, the distance from O is essentially asking for the displacement. Remember, distance from a particular point, when it's in one direction, it's same as the displacement. They're asking for this bit here. So really what we need to do is substitute that time value that we found into particle P or Q because they both have that same S. It doesn't matter which equation we use. So go and substitute that into one of the equations. I'll substitute in here. S is equal to 12, 1.4 minus 4.9, 1.4 squared. Okay, and when you do that, the